Okay, hello everyone. So hope you're all doing good. Myself Ravi, and in this session we are going to talk about we are going to explore about K-nearest neighbors algorithm. And K-nearest neighbors is one of the widely used machine learning supervised machine learning algorithm in different industries. And of course we are going to talk about introduction about the KNN and what kind of distance metrics were involved in KNN, and we are going to see some practical implementation only from the mathematical perspective, not from programming perspective. But you can use the KNN library directly from the Lotus ML package, and we will discuss about the results of the practical implementation, and then we will come to the conclusion of this of the experimentation process we have conducted in this uh, in this session. Of course, like I told you, both the K-NAN introduction, K-NAN is one of the widely used supervised machine learning algorithm. You could also use K-NAN for different kind of problems, such as maybe regression and classification problems. So in the regression problems, uh, maybe I can give you some simple example for your easy understanding. So let's say if I'm sitting in a library and I want to get my lunch, so I'm looking for two different, I'm looking for supermarkets near me. So I have two supermarkets near to my location. And one of the supermarket is zero point 0.3 miles away from my location, and another one is zero point 0.6 miles away from my location. So in this regression case, in the regression perspective, I can choose the supermarket, whichever one is closer to my location. So in this case, I have the supermarket one is nearby to my location, which is zero point 0.3 miles away. So in this case, that will become my prediction. And this is about the K-NAN regressor and about the K-NAN classifier. Let's say I can give you another example for this use case. Let's say we have two baskets, and both basket contains apples, and one basket contains 15 apples, and another one contains 30. And in this case, I have to take which basket has the more apples. So in this case, I have the second basket, which has 30 apples, which is comparatively higher than the first basket. So in general, in classification, you have to consider the majority of the instances, and the regressor, you have to consider which one is closer to you know, your actual value. And about the classification, like I told you, we need to consider only the majority of the instances of the classes. So in order to find out this process, we can use a different distance metrics. We can use Euclidean distance, Manhattan, Minkowski, Levenshtein, or cosine similarity. There's so that we can experiment with. We will talk about this later in the coming slides. And for the K-NAN regressor, like I told you, we need to find out whichever one is uh, closer to our actual values. So for example, in K-NAN regressor, you need to specify the n neighbors or k values, and maybe I will give you some example. Let's say if my uh, based on from the previous example, if I'm sitting in the library and one of the supermarket is zero point 0.3 miles away, and another one is zero point 0.6 miles away, and the third supermarket is you know zero point 0.2 miles away, and the fourth supermarket, which is 1.37, 1.31 miles away. So if I specify the k value equal to 3, then I will get the first three shortest value. In this case, the distance with the units 0.3, 0.2, and 0.6 will become my will consider for the experimentation. And from these three instances and these three units, I can pick whichever one is has the shortest value. And the advantages of the KNN, no, it's very, sorry. I mean, it's very easy to interpret your prediction because it's, yeah, you don't have to complicate anything uh, for interpreting your predicted results, and it does not make any assumptions since it is more processing on the real well, real data. And one of the and some of the disadvantages in Kden or Kden takes a lot of memory, computation power, which takes too long time and it's computationally expensive. And if we select the K value, in larger units, then of course it will affect the model performance. Like I said, it will take more computation process. So, and another very interesting, you know, uh, definition for, I mean, one of the disadvantages is since our data set might have some extreme values or outliers, K then could also consider those outliers as a predicted value. If the outlier value is closer to our target, it will even consider as a predicted value. That's one of the main drawback. And yeah, and also bias. So if we have anything like if our data set is imbalanced, like for example, if class A has belongs to 10 instance and class B belongs to 15, then we can say there is an imbalance because we need to have uh, equally or equally shared instances. So here comes the main part, and of course in Kden we can use different distance metrics, and one of them is Euclidean distance, Manhattan distance, and Minkowski distance. So in Euclidean we will take the sum of square difference between the target value with the actual value, and then we will take the square root of the final value. And in the Manhattan distance, which is same but it's a different process, but slightly different, we will perform the difference between the actual and the predicted value, and then we will find out the absolute value as a result. With Minkowski, it's a different case. Of course, we will take the difference between the actual values and the predicted values and the actual value, and then we will take the absolute uh, operation. Op- yeah, and then we will square it with the n number of values, and then we will take the version of 1 by n number of samples. So as you can say, you can also ask me like when we can use these distance metrics. So if, for example, if we take Euclidean distance, we can implement this Euclidean distance when we have same units in the future. Let's say, for example, if we have one future that belongs to centimeter and another future also belongs to centimeters, then you can use Euclidean since it is based on same units or it is continuous. And in Manhattan, you can use it when you have different units. For example, if you have one future related to kilometers and another future related to miles, since those are, of course, both represents a distance but can be measured in different units. So we can use Manhattan and Minkowski. You know, both can we can use this when we want to control the sensitivity of the data of the future. For example, if you want to scale your future to some extent, you can use Minkowski because Minkowski is more like you can specify the n number of samples, and also you can also add p as a weight, in which in this case we can add p equal to n. And this is about our dataset, which just I created just to give you some general example, like easy for you to understand. So I created only 5 samples with the house. We have 5 different house with the 5 different square feet units, and we have different specifications for bedrooms and bathrooms. And finally, we have price. So this is what we need to find. So based on these square feet, bedrooms, and bathrooms, we will predict what will be the price of the requested futures. And the problem we need to solve for this project, it's like we need to build a Canaan model to predict the housing price based on our data set. And of course, it's I will leave the second step up to you, because you need to check whether is there any null values present in our data, or is there any duplicated features present in our data. If there is such kind of error, you know, if there is such kind of inconsistencies, of course you can fix it with the mean imputation or median imputation, yeah, things like that. And if you have any duplicated features, you can drop the one particular column. And of course, we are going to experiment with the one of the distance metrics. So in this case, we have all of those values represented in the same units. For example, we have square feet, which is also same as which is also in the same unit, and bedrooms you have in the same unit, and bathroom you have it in the same unit. And yeah, and experimentation. So in this case, our dataset has 5 features, so we can say that our data are represented in 5 space or in 5 dimension. Since our dataset doesn't have very enormous amount of features, so we don't need to perform any principal component analysis or any other dimensional reductionality techniques. And of course, we can only consider the features related to square feet, bedrooms, and bathrooms, because that's what going to use, and then we are going to predict the price of your requested uh, features. And for the price prediction, we will sum up all the features, and which will be divided with the total number of shortest values. So here comes the first step in the experimentation. Like I said, we are exploring only from mathematical perspective, not from the programming, because you need to understand the black box techniques behind each and every ML algorithms, because machine learning is entirely based on mathematics and these things. So let's start with on the left side we have specified the k value equal to 3, and let's perform the first experimentation, which uh, yeah, before that you can find one separate table. This is our the requested inputs that we are going to compare it with our actual values here. So in this case, x will become 2000. So first we are working on the square feet, and then we will compare it with the first instance to 1500, and then we will square it, and then we will compare the bedrooms 3 with the first instance with the bedroom 3, and then we will compare the bathroom first instance 2 with the bathroom first instance 2, and likewise we can compare the the value we want to, I mean the input, with the square feet here, 2000 minus 2000. Likewise we can continue for all the 5 instances, and after computing these values we will get 500 for the first instance, and then we have 1 for the second, and we have 200 for the third instance, and we have 400 100 100.1 for the fourth instance, and for the fifth instance, sorry, there's a typo because I just mentioned it as 4, it will be 5. So in the fifth instance it will be 400 unit. And based on the shortest value, we can say the second instance, third instance, and the fourth instance or shortest uh, has the shortest values. So in this case, the house, we will consider the house 2. I mean with this one, house 2, and house 3 and house 4. Yeah. And based on from the considerations, we will know all of the prices, um, based on the house 2, house 3, and house 4. And if you want, we have specified the prices listing here, so don't get confused. So we will consider the price from the house 2, house 3, and house 4, and we will sum up all these three together, and then we will get a value 870k. And then we need to, and then we have specified the k value equal to 3, and which we will divide it by 3, and then we will get the new house price 290k for this for the 2000 square feet unit, and for 3 bedrooms and for 2 bathrooms, and this will be our predicted price. And from the visualization, as you can see, in the x-axis we have the prices, and in the y-axis we have the housing property. So for the first house, the price was 250k, and the new house I have requested based on the 200 square feet units and 3 bedrooms and 2 bathrooms. The prices will be like 290k in dollars, and this is how we can interpret from the visualization. And to conclude this entire experimentation, so based on the three n neighbors value or k values, and on based on the input requests related to 200 square feet and 3 bedrooms and 3 bathrooms, it predicted the the price of the requested futures will be, and requested property will be 290k dollars. And some of the reference I have taken for the distance metrics from this scientific paper. And thank you. So if you have any questions, just you can leave a message. You can find it in my website. Yeah. Thank you. Cheers. Bye.